Yes, very good afternoon, everyone. So today, I'd like to discuss about the nonlinear data structure, another nonlinear data structure that is graph. Is the screen visible to you?
It's visible.
Yes, sir.
Yes,
Yes.
sir.
Fine. Okay.
Yes, sir.
Fine. Thank you. So, so we will discuss today the basic things regarding the nonlinear data structure graph. What is a graph and various properties of graph we will see in this presentation. Edges that are relate the nodes to each other means like the trees actually we can also call it as a graph which has no cycles. So what is the difference between the tree and the graph? Here is the tree has no cycles, whereas in graph we may have a cycles. What is the cycle? We will understand very soon. But it is a nonlinear data structure which consists of nodes, vertices, and also the set of edges that relate to each other. Means there is a relation between those nodes, and they are related. And there will be an edge. And the set of edges describes the relationship among the vertices. So you have the number of edges, vertices which you can find, and these sorry, there will be number of edges which you can find, and these edges will describe the relationship among the vertices. And graph G can be defined as G is equals to V, where V of G is a finite non-empty set of vertices. So V of G defines the vertices, the finite non-empty set of vertices, whereas E of G will define a set of edges, the pair of vertices, set of edges, the pair of vertices here. Next, the example here, you can see one example here. So we have the edges which are 0, 1, 2, 3, 4, 5. These actually forms the edges there. And the vertices here, there is an edge between 0 to 1. There is an edge between 1 and 2. And there is an edge from 0 to 3. There is an edge from 0 to 3 once again. Okay, there is an edge from 4 to 3, and there is an edge from 2 to 2 itself. So here, these are all means the set of edges which forms a graph is defined as V of G, and the set of vertices which are taken in the graph forms the vertices. And when x comma y is an edge, when you call an x comma y as an edge, that we can say that ax is adjacent to y and y is adjacent from x. If there is an edge from x to y, then we can say x is adjacent to y and y is adjacent from x. So here from example you can observe that 0 is adjacent to 1 and 1 is not adjacent to 0. So we cannot say that 1 is adjacent to 0. We can say 1 is adjacent from 0. We can say that 1 is adjacent from 0. We cannot say 1 is adjacent to 0. Whereas 0 is adjacent to 1. And now likewise 2 is adjacent from 1. You can say that 2 is adjacent from 1. Next, we have the directed and undirected graph. The next set of definitions is directed and indirect graph. So an undirected edge has no orientation, that is no arrowhead there. There will be no orientation there. In either way you can visit from here, either edge U to edge V or V to U. Both ways you can have, so you can go. And whereas in case of directed edge, you can have that arrowhead, means which way there is an orientation. You can see here a directed edge is from U to V. And an undirected graph, when you call a graph as an undirected graph, if all the edges are undirected, then you call it as an undirected graph. Whereas in directed graph, all edges are directed. So there will be two types of graphs here. One is undirected graph and a directed graph. So if it is an undirected graph, there won't be any, all the edges will be undirected. Whereas directed graph, all the edges will be directed. Next is after this weighted graph. So a graph can be a weighted graph if each edge carries some value. A graph is called as a weighted graph if each edge carries some value. If there is some value which carries if there is a value which is mentioned along with the edges, then it is called as a weighted graph. Okay. Now here this weight, the value, how you are specifying the value, on what basis you are specifying the value, that depends upon the condition there. So here, see for example, from asked, see an example here that an Austin to Dallas is mentioned as 200, and from Dallas to Austin is mentioned as 200. Okay. The likewise you have from the last to some Denver, it is 780. Now, what is this 780, or what is this 200, or whatever the other figures which are mentioned here? No, it depends. It depends upon the situation there. So, what I can say that is you can place the number according to some cost, the cost of traveling, or you can say according to some distance or some other factor which you want to mention. Okay. So that depends upon the graph which you are building them. Don't think that here the value may be the cost. Generally, it is mentioned as a cost. So cost in the sense it is not only the monetary friends. So sometimes you can have the value depending upon the distance or some other factor there. So like in graph theory, I hope in your discrete mathematical structures also you're having the graph theory where you will be learning about these graph, and also finding the shortest distance, shortest job first. Okay. There will several algorithms which are there. Hopefully, we will cover some of them in this coming classes also. Okay. Next is the directed graph. Again, it is given here that see the directed graph edge ij is incident to. Means here directed graph ij is incident to vertex j and incident from vertex I. So you can say if there is a directed edge here, an edge here from I to j, we can say that it is incident to vertex j and incident from, means from is specified from where it is starting and to is where it is going. So I can say that it if I say take an edge from 1 and 2, I can say that incident to 2 and incident from vertex I, incidence from vertex I to incident to the vertex j. Likewise, you can mention the mm, other directed edges here. Like vertex I is adjacent to vertex j, as it is mentioned earlier that vertex I is adjacent to vertex j and vertex 2 is adjacent from vertex 1 here. So if I take this edge 1 and 2, 1 to 2 there, I can say that 1 is adjacent to 2 and 2 is adjacent from 1. Likewise, I can say 1 is adjacent to 4 and 4 is adjacent from 1. So in general, we can say that vertex I is adjacent to vertex j and vertex j is adjacent from vertex I. Okay. So this is another graph which is given here, which is undirected, where there is no arrow pointing to there. I can take an edge as 1 to or 2 from 1 to 2 or 2 to 1. Next, next we have uh, the graph terminology, the various graph terminology which we are supposed to understand. So what are the adjacent nodes here? As two nodes are said to be adjacent if there is an connected by an edge. If nodes are said to be adjacent if they are connected by an edge. So I can say this, say 5 and 7 are connected here. So 5 is adjacent to 7 and 7 is adjacent from 7 is adjacent from 5. Then you have a path. A path actually a sequence of vertices that connect two nodes in a graph. A path specifies a sequence of vertices that connects from uh, uh, two nodes in the graph. So now here I can say what is the path between 1 to 7. If someone asks that what is the path between 1 to 7, so I can say you can have 1 to 2, 2 to 5 and 5 to 7. That is the path between 9 and 7. Likewise, what is the path between 9 and 7 there? 1 to 4, 4 to 6 and 6 to 7. So this is actually completes a path. So the path is a sequence of vertices. So connecting two nodes. So I can say 1, 2, 5, 7, or I can say 1, 4, 6, 7. Okay. So if suppose it is 1 to 3, so then I can say 1 to 1, 2, 5, and 3. So like you have a sequence of vertices that connects a graph. A simple path is a path which in which all vertices except possibly the first and last are different. A simple path is a path in which all the vertices except the possibly the first and last are different. So if it is different, the first and last are different, then it is called as a simple path. Okay, means sometimes you may start. I mean, why it is mentioned like that is you may start and you may want to end to the same point. So in such case, the first node and possibly the last node will be the same. So in such case, first and last are same. In between, whatever the nodes which are mentioned in the path, those all may be different. Then you have a complete graph. What is a complete graph? Graph in which the vertex is directly connected to each other vertex. So when you call a graph as a complete graph in which every vertex is connected to every other vertex. So if there is an edge between each pair of vertices here, then it is called as a complete graph. Then we have cycle. As I just said, I mentioned earlier about this term cycle. The cycle is a simple path in which the same start and same and in which the simple path with the same start and end vertex. So the beginning and the ending vertex, if both are same, then you call it as a cycle. And next is, what is the degree here? What is the degree? Degree of a vertex I is the number of edges incident on vertex I. So the degree of and vertex I is the number of edges incident on the vertex I. So if you take any vertex there, so how many edges have been incident on it is mentions the degree. So you can say, observe here the degree of 2 is 2 because 2 edges are been incident on 2 there. Likewise, if I take the degree of 5 is 3 because 3 vertices are been adjacent on incident on vertex 5 there. And degree of 3, if you observe here, the degree of 3 is mentioned as 1 because only one edge is incident on vertex 3. Okay, next. What is undirected graphs are connected if there is a path between any two vertices. So if there is a path between any two vertices, then undirected graphs are connected if there is a path between any two vertices. If there exists a path between any two vertices, then it is called as a connected undirected graph. Whereas directed graph are strongly connected. When you call a directed graph as a strongly connected, if there is a path from one vertex from any one vertex to any other vertex, if there exists a path between one vertex to any other vertex, if suppose a graph is there, and assume that there exists a path between from one vertex to any other vertex, then it is called as a strongly connected graph. Now here, if you observe in this figure, so there is a path between 1 to 4, 4 to 6, and 6 to 7, but there is no path between 7 to 6, 6 to 4, sorry, from 7 to 1. There exists a path between 1 to 7, but no path existing between 7 to 1. So such a graph is not called as an strongly connected graph. Okay, then you can have a directed graphs are weakly connected if there is a path between any two vertices ignoring the direction. So if you ignore the direction and if there existing a path between any two vertices, then you can say that it is a weakly connected graph. And when you call it as a complete graph has an edge between every pair of vertices. When there is a path between every pair of vertices, as it is mentioned here, so a graph in which the vertex is directly connected to any other vertex, then it is called as a complete graph. Next, the loops. As I told, if next definition here is about the loops. What is a loop? Loop edges that connect a vertex to itself. If an edge is connecting to the same vertex, then it is called as a loop. So in previously in one figure there is a loop you observe. So here it is. 2 is connected to 2. 2 is again connected to a 2. Then it is called as a loop here. Next. is path. Sequence of vertices. What is another terminology here? Path is a sequence of vertices PO, P0, P1, so on to PM, such that each adjacent pair of vertices are connected by an edge pair. So in this, each adjacent pairs of vertices are being connected to one another. Then such is called as a path. And a simple path, as mentioned earlier, is a path in which all vertices except possibly the first and the last are different. If first and last are different, then it is called as a simple path. And multiple edges are those two nodes may be connected by greater than one edge. If two nodes are connected to same one another greater than one, then it is called as a multiple edges. So here, say if you observe, uh, yes, from 0 to 1, sorry, 0 to 3, it is connected twice. From 0 to 3, it is connected twice. Then it has multiple edges, means there is a path between 0 to 3 multiple times. Then it is, can be termed as multiple edges. And simple graphs has no loops and no multiple edges. You can call a simple graph as a graph with no loops, means there won't be any edge from a node to a node itself, and there won't be any multiple edges. Such a graph is called as a multiple simple graph. Then some more properties of graphs is number of edges in an undirected graph. So how many number of edges will exist in an undirected graph? So the number of possible pairs in an n-vertex graph means if there are n number of vertices existing in the graph, then the possible number of pairs of edges pairs in an n-vertex graph will be n into n minus 1. N into n minus 1. So since edge UV is same as edge VU, okay, as edge VU, the number of edges in an undirected graph will be n into n minus 1 by 2. The number of edges in an undirected graph will be n into n minus 1 by 2. Since because the same, because here 1 to sorry, A to B is same as B to A. If I take A to B is same as B to A, then you can take it as one count. Then the number of edges will be n into n minus 1 by 2. So here, if you observe, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 edges. So 9 into 9 is 72. We can at most form 72 number of pairs here. We can form 72 number of pairs here, and then in that we can have only 72 by 236 number of edges in case of undirected graph. Then you have number of edges in a directed graph. So how many number of edges will be in a directed graph? The possible number of pairs in an n-vertex graph will be again n into n minus 1 by 2. Okay, so there will be possible number of edges will, as mentioned earlier. Here also it will be n minus n by 2, n into n minus 1 by 2. Since now here the edge UV is not same as edge VU. Previously both edge UV and VU are same. N into n minus 1 edges there. It may be less or more, but possibly there will be less than or equal to n into n minus 1 number of edges in case of directed graph. Next you have the in degree and out degree. Other two properties to mention is about the in degree, out degree. The in degree of a vertex I is the number of edges incident to I. So how many number of edges incident to I will be in degree, means the number of incoming edges. So how many edges are being coming to it, coming to a particular vertex will form the in degree, and out degree will be the number of edges incident from I. So how many edges are incident from I will give the number of outgoing edges there. So for example, the degree of 2 here, if you take the degree of 2 will be 1, because okay, because I'm audible.
Yes, sir.
Yes, sir.
Okay, okay, okay. Fine. So out degree is an vertex I is a number of edges incident from I. So if you observe, the in degree of 2 is 1, because the incoming edge will be 2 and outgoing is 1 there. In case of 8, if you take 8, the incoming is 0 because nothing is coming to it. So in degree is 0. Uh, uh, the number of edges incident to 8 is 0, whereas the number of edges incident from 8 is 2. That's the reason why the out degree of 8 is 2, whereas the in degree of 8 is 0. Okay. Likewise, if I take what is the in degree of 5, the in degree of 5 is 1, whereas the out degree of 5 is 2. Because from 5, there forms an edge as 5 to 7, 5 to 3, but to 5, an edge is coming from 2. That's why the in degree of 5 is 1, whereas the out degree of 5 is 2. Okay, next. So actually, the graphs have been represented in the memory. The next point of discussion here is how the graphs can be computationally means represented in the memory here. So for the graphs to be computationally useful, they have to be conveniently represented in the program. There are two computer representations of the graphs. In two ways, we are supposed to represent the graphs in the memory. One is adjacency matrix representation. The other one is adjacency list representation. You have the adjacency matrix and adjacency list representation. So what are these two here? So adjacency matrix representation, it is a square grid of Boolean values. An adjacency matrix is a square grid of Boolean values. Square grid of Boolean values in the sense here you will have a square matrix, an array of means a square matrix which has the Boolean value. Boolean values in the sense Boolean will take only two values, either true or false. Okay, so if there is an edge from a vertex I to vertex j, then it will be true. If there is no edge from vertex I to vertex j, then the entry will be false. So in the graph of n vertices, the grid contains n rows and n columns. Obviously, suppose a graph contains three vertices, vertices in the sense there will be 3 into 3, 9 entries will be there. If two vertices numbered I and j, the element of row I and column j is true if there is an edge from I to j, otherwise false. As I just said, if there is an edge between an vertex I to vertex j, then you have an entry as true, otherwise it becomes false. So here is a matrix, adjacency matrix. So see here, so you have 5 vertices here. So vertex 0, vertex 1, 2, 3, 4. So you have a matrix of 5 into 5, 25. Now from 0 to 0, there won't be any edge because there is no loop here. Now from 0 to 1, there is no edge. Again, it is false. From 0 to 2, there is an edge. That's why it is mentioned as true. Likewise, there is no edge from 0 to 3 to and also to 4. That's why both are mentioned as false. So if you take 2, the vertex 2 is there. So for 2, from 2 to 0, there is no edge. Whereas from 2 to 1, there is an edge. So that's why it is mentioned as true. Then you have 2 to 2, no loop. So false. 2 to 3 also, there is no edge. And whereas 2 to 4, you have an edge. That's why it is mentioned as true. So like that, you can construct the entire matrix here. So Boolean values, you can take 0 to 1. 1 is mentioned as true and 0 is mentioned as false. In such case, the matrix will look like this. Okay, so you have 1, 2, 3, 4, 5, 5 numbers. So because it is an undirected graph, for 1 to 2 also 1, and from 2 to 1 also there is 1 there. Previously it is a directed graph, so that's why its representation is like this. So in case of undirected graph, you can mention both true, whether it is from 1 to 2 or 2 to 1 entry. Okay, here one small example is given. An example is given that for a directed multigraph. If it is a multigraph in the sense if there are multiple edges from one node to another node, then we have the multigraph there. And if you observe very clearly from 1 to 2, from 1 to 2, actually the number is mentioned as 3, not as 1 there. What does that mean here? Because from 1 to 2, there are 3 edges which are mentioned here. Because three edges have been mentioned here, that's the reason why the value is mentioned as 3. And from 1 to 4, there is only one, that's why only one is mentioned. Then you have 2 to 1, there is no edge, and 2 to 2, because there is a loop, that's the reason why uh, 1 is mentioned. And from 2 to 3, actually you have through two edges, that's why the mention is as 2. And from 2 to 4, there is nothing is there. And from 3 to 0, the same, 3 to 1, no edge. 3 to 2, there is one single edge. 3 to 3, because we have two loops here, that's the reason 2 is mentioned. So by likewise the remaining also. So you can take the construct an adjacency matrix graph like this, and you can represent it in the memory. Then adjacency list representatives. Actually, adjacency list, if we talk about the adjacency list here, so it is actually talking about the linked list. So you have an one-dimensional array. It is represented using a one-dimensional array L of linked lists here, where L of I is a linked list containing all the nodes adjacent from node I. So you have array means each node actually has a linked list which actually has the nodes which are adjacent to node I, and the nodes in the list of I are in no particular order. There won't be any particular order here. There will be a different order. So, for example, here you observe that adjacency list actually each vertex V belongs to store the list of vertices of adjacent to V. For example, adjacent of 1. Who is adjacent of 1? 2 and 3. Adjacent of 2 is 3. Okay, adjacent of 3 is null, and adjacent of 4 is 3. So they can variation can also keep a list of edges coming into vertex X into vertex. So you can have a list of edges which are coming into, like all means just here mention all the vertices which are going out. Out degree is mentioned here, but whereas in case of in degree can mention. Now the same thing here, how much storage is required? The degree of vertex V equals to the number of incident, means if you want to have the adjacency list here, so how much storage is required? The degree of vertex V is equals to number of incident, which is directed graphs have in degree and out degree. Generally, the degree of vertex V is equals to the number of incident, which is how many edges have an incident here. So in case of directed graph, you have an in degree and out degree. For directed graph, number of items in the adjacency list is sigma of out degree of V is equals to the modulo of E value there. Whereas in case of undirected graph, the number of items in the adjacent list will be the degree of V is equals to 2 times the number of edges, 2 times the number of edges. So adjacency list takes an order of V plus E storage. It takes an order of V plus V. So you know the big O notation which you are learning in your what is that DA subject there. So if you calculate the order of how much storage it is going to take, it is going to take the order of V plus E. Next, this is the implementation graph here. Another graph which is given. Okay, so the values 0 to means P to P. Where's the P to P? 0 means here the order is mentioned 0, P, Q, or the numbers are given in the matrix. So P to P is 0, then P to Q is 0, P to R is 1, P to S is W, sorry, P to S is also 0, and P to T is also 0. So like that I can consider the remaining graph. And implementation of a graph using the adjacency list matrix. One is adjacency matrix and adjacency list. If you come out, so now here it is 0, A, B, C, D, all an array of all the vertices have been directly taken, and each one now is a linked list. Each one is also is a linked list. See, there is an edge from A to B and A to D. So A is connected to a node which has the B value and its weight, as well as a pointer which has an address of next node. Then it has a uh, uh, D with the value 6 there, and there is null. So this doesn't mean here one thing you observe that this doesn't mean that B is having an edge to D. See, there is no connection between B and D there. The meaning of this first row here is there is an vertex called A, and from vertex A, two edges have been formed. One is from A to B and A to D. So that is actually the list is been maintained here. Likewise, from B, you have an edge to A as well as C. That's the reason why it is mentioned as A and C there. And don't think that you have to follow the same order. First you can write C, then you can write A. Or here also first you can write D, then you can write B. But from C to B, sorry, from C, there is only one edge. That's the reason why it is mentioned as B. And from D, there is only one edge to A. It is mentioned as A. So a weighted undirected graph and an adjacency list can be maintained or can be mentioned like this. Okay, so that is about the graph, the basic terminology which we are supposed to practice and know. So in the next class, we will discuss about mm, what I can say. We will discuss about the other traversing techniques under the graph theory, how we can traverse various nodes, and what else we can do under the trees and graphs. We'll discuss in coming classes. So, any doubt?
No, sir.
No, sir. No, sir.
No, sir.
Okay. Prasad is
Sir.
having any doubt?
No, sir.
Hmm.